So first of all, something kind of cool to let you guys know about, maybe something to look forward to. Every year, the computer science department, we compete in several hackathons. Hackathons are the general format is you go somewhere, you get locked into a building for 24 hours, you are given a kind of a generalistic mandate, like create a mobile application that helps this cause, or sometimes there's clients that are there and they say each client gets up, gives a 10-minute presentation and says, we're looking for an app or a program that does this. And then each team can pick one of the clients, or two teams can pick the same client if they want. And they, for 24 hours straight, they build that project and then submit it, and there's prizes and food and stuff like that. So, it's a cool thing. Last year we did 2 of these, and we brought 2 teams, and the students split first and second place. So that means between all the students, they split $8,000. So kind of a cool thing to think about. We're going to one a week from Friday. I'm taking the guys down. Sometimes I compete with them, so they have some sort of programming competence type support. Because we try to bring seniors, and we also try to bring like sophomores to give them some experience. So we're going to one in Iowa here a week from Friday, and we are bringing down 3 sophomores and 2 seniors. They've already been selected. It's from the 250 class and the 300 class. Actually, they're all from the 300 class and then senior seminar. And so this one, I don't know what the prize money is. It might be like 10 grand or something for first place or something like that. But I'm not competing in this one. I'm going to just do a little vacation weekend with my wife while we're down there, and I'll be tech support if they have a question how to do something. But I think we're going to be doing one in June in Chicago. That's actually a pretty big one. That is I think it's a $10,000 regional prize. So if you win it, you get 10 grand. But then if you win it, you qualify to go down to Silicon Valley for the $100,000 hackathon final or something like that. Regardless, it's not necessarily about winning. It's about the cool experience of being around other computer science students, other, computer science people who are competing in these. And so something to look forward to if that sounds of interest to you. We try to do at least 1 or 2 of those a year. I suppose for those of you who are interested, the one in Iowa, it's a week from Saturday. We're going up the a week from Friday. It's open. It doesn't cost anything to get into the event, but the department's paying for this team to go down. If you'd like to go down for it, you can figure out your own arrangements. Drive down to Iowa. It's like a 7-hour drive. Yeah. And go and do it and experience it. And they give you plenty of energy drinks and food and stuff like that to spend the whole night there. But in any case, just figure I'd let you know that that's something that we try to do at least once a year, sometimes several times a year. And we've had some success with those, but regardless, it's a kind of a cool experience. Go ahead.
Can I ask where it is now?
It's right outside of Des Moines. I think it's the name of the actual town is like Anke. I'm going to make up the last 3 letters. Yeah. Yeah, it's like 10 minutes from Des Moines.
Okay.
Is that?
I go to Des Moines all the time, so that's how it's going. And also, Josh and I are in Iowa next week, or the same weekend for nationals for wrestling.
Okay.
So I was wondering if it was close, maybe we could just stop by or something. But
Yeah.
It's not, so
Oh, it's
3.5 hours away.
Oh, I got you. I was gonna say if you're gonna do it, then you might, if somebody wants to put together a separate team, I'll be down there anyways. I mean, I can be in your guys' team. We can beat the team we're bringing down. Not to toot my own horn, but I do tend to benefit the team I'm on. I'm better at regular programming than Game Salad. The matrix of Game Salad tends to be problematic. Okay, so any questions about that? Kind of a cool How many of you think that's stupid? My hope is most of you think the hackathon thing at least sounds cool. But does anybody in here actually just think that sounds completely dumb? Like, why would a bunch of geeks trap themselves inside of a building drinking energy drinks to write programs? Most of you are going to go. Okay. Today, we're going to kind of pause our. Shut up! We're going to pause our launch monitor thing just for a day or so, and do a kind of a secondary exercise. I want to kind of get back and connect some things to Java, because right now we're in a little bit of a rut with the launch monitor where we're playing in the matrix, which is all fun and games. Nothing wrong with that. Figuring out how where we're going to next with that is some collision stuff. And how we can use collisions with hidden things and maybe make things work. But rather than play around more with the matrix, I want to go back to a little bit more of a programming type exercise. So we're going to introduce, I'm going to do a little Java, and then we're going to also then go back into GameSolid and write the equivalent. So, well, again, reminder, this Sunday, after daylight savings time.
Good.
All right.
I have a question about that as well.
Yep.
I heard that one of the guys from the 450 class asked you about the men's retreat.
Mm-hmm.
That's this weekend. Are you giving out just one quiz grade for that or two?
One.
Okay.
So if you are going on the men's retreat and you send me evidence that you're going or whatever, I will excuse you from the presentation portion of the thing, and you'll get the extra credit from that. Because I want to support the men's retreat as well. Okay. Was it coleslaw? Who told you that? Coleslaw?
No, Jake Van Kyle.
Oh.
My roommate.
You know coleslaw, don't you?
Yeah. Yeah, I work with him. And actually, Ryan was the one who told me about it.
Okay.
What if Beaker?
Beaker, yeah. Everybody, all of you will get pet names by the. Well, not all of you. Only some people. Only special people get pet names. So we have Beaker, we have Coleslaw, we have Tina, who's actually a dude. That one goes back to freshman year. It's historically we had a guy named Shira. That's before all your time. His name was Ronique Rose. He was a football player, kind of a shorter guy, but like ripped, like always in the gym and stuff like that. But he wasn't He-Man buff. He was more like She-Ra buff. So became She-Ra. At the end, by his senior year, he was signed as Test She-Ra. Whole football team was calling him She-Ra. I'm sure I stunted his growth. But I never give nicknames to somebody who hasn't already shown they're good sports about stuff like that. I don't want to. We got a guy that sits right here in the 300 class who's called Amish. Yeah, that was day one of 200, actually. Day one of 200, he said something that I asked about some TV show. He said, I don't watch TV, so no TV, no electricity must mean Amish, right? So now every single class, we were talking about he's actually one of the ones coming down to the hackathon with us, so he's going to bring his stone and chisel and laptop, the Amish laptop. We were talking about whether or not we should carpool down there or drive separately. He didn't think his buggy can make it. And another student last year brought in a funny video from Family Guy. There's like an Amish. Here, I gotta look it up. This is a good one.
How come Angel's not working right now either? Do you have any idea?
No.
What?
Another DDoS attack. No, I would expect Angel would.
That's the area.
Okay, here it is. All right, so keep in mind that this is, about 6 months into this guy being called Amish. We've made a zillion jokes and stuff like that. Then randomly somebody brings this video into class.
Suck on this, you furry little weirdos! Enough of this crap. Ezekiel.
It'd be funny, like all of them step forward. All right, so yeah, we'd already made all the barn jokes, so it was okay. So now that we've had the entertainment, let's talk about some programming stuff. So we're going to talk about just a function called factorial. All right, so factorial, usually designated something like that with a little exclamation point after it. So 4 factorial is actually 4 times 3 times 2 times 1. Right? Okay, so that's the, what's that, 24? All right, so if we're in Java and we're writing this function, so we're going to write this function 2 different ways in Java, and then we're going to go and we're going to simulate it in GameSalad. Okay, so in Java, we have these things called methods. So methods are reusable chunks of code. Okay, so we can store a bunch of logic inside of a single method and call it as many times as we want. Historically, these guys were called subroutines. They were called functions/procedures. This was from older languages like Pascal. A function is a method that returns a value. A procedure is a method that does not return a value. Modern day languages, object-oriented languages, call them methods. So that's an object-oriented term, methods. And they have a return type, and you specify whether it returns something or not. If it's not going to return anything, you just make the return type void. If you're going to return something like an integer, you set the return type to integer. Okay. So anyways, this is kind of the history of methods. So we're going to write one of these guys for solving factorial. And it's going to use a loop. Okay? And it's going to use questions. So remember back to our how do human beings solve problems. We need to remember things. We're going to have a variable in there. We need to ask questions. We're going to ask some questions with if statements. And we need to be able to repeat things. We're going to do some repetition with the for loop. Okay? So I'm going to write this little function down here. Call this guy factorial. He returns an integer. And don't worry about the static thing. We talk about that next semester a lot. Okay? And factorial is going to take in an integer to work on. So what we've essentially done there is we're solving the problem of n factorial. N factorial is n times n minus 1 times so on and so forth to 1. Make sense? Okay. So we'll ask the question. Well, we're going to create a int answer. We're going to start this guy off at 1. We'll create a for loop. So we'll start at, and we're not going to start at 4, we're going to start at whatever n is. It would be 4 if we were doing the factorial of 4. In this case, we're going to start at n. Okay? So we're going to start, this loop goes through so many times. This says, start I off at whatever n is. Keep going as long as whatever I currently is greater than 1. Subtract 1 from I each time. And we're going to build our answer inside of answer. Okay, so the first time through, I is, if we were doing this for factorial of 4, for example, I would be 4. Is 4 greater than 1? It is, so we'll take answer, set it equal to whatever answer currently is, which is a 1, times 4. So answer will be 4 after the first pass. Next time through, 4 becomes 3. Subtract 1 from it. Is 3 greater than 1?
Yes.
Yes. So we're going to take answer equals whatever answer currently is, which is 4, times 3, which is 12. Loop back up. 3 becomes 2. Is 2 greater than 1? Yep. Go back down. Answer is equal to whatever answer currently is, which is 12, times 2, which is 24. Loop back up. I goes from 2 to 1. Is 1 greater than 1? It's not. So we'll fall past the end of this loop, and we'll return our answer, which holds the factorial in it. Make sense? So this code now generically works for solving the factorial of any positive number. So we'll go ahead up here and print out system.out.println scene.factorial of 4. So that'll give us the factorial of 4. We'll do a factorial of 5, which should be, I think, 120. So there's our 24 and there's our 120. So using the same chunk of code, we solve for 2 different factorials. Make sense? Okay, so that is what's called an iterative solution. Well, here, let's just do types of solutions. Iterative typically uses a loop to do something a certain number of times. Another type of solution is a recursive solution. Now, factorial works very well for recursion. That's why we choose a simple little function like that. So the idea would be this. Well, here, let me give you the definition of recursion first, and then we'll go and look at how to do it. So a recursive solution, a method that calls itself from within itself. So the loop is built into multiple method calls. Okay. As an example, if we go back to factorial, 4 factorial is actually equal to 4 times 3 factorial. 3 factorial is actually equal to 3 times 2 factorial. 2 factorial is actually equal to 2 times 1 factorial. 1 factorial is actually equal to 1. Does that make sense? So to solve 4 factorial, we're going to take 4 and we're going to multiply it whatever our factorial returns for 3. To solve 3 factorial, we'll multiply 3 times whatever our factorial returns for 2. To solve 2 factorial, we'll multiply 2 and multiply it by whatever our factorial returns for 1. So on and so forth. Then everything unravels. The recursion unravels. So let's write the recursive version of this guy. Let's call this fact R. Take an n as a parameter. So that's the whole function. I purposely left out a bunch of curly braces and stuff that are optional just to show you how much shorter recursive functions tend to be. Okay, so we're going to take an n. If n is equal to 1, return 1. That's the end of our recursion. Otherwise, return n times the factorial of n minus 1. This line cannot finish until we get an answer from this portion of the line. That make sense? Okay, so what do I call that? Fact R. We should get the same answers. It's our 24 and our 120. Okay, so two different ways of solving the same problem. And we can probably come up with a couple of other iterative ways of solving the problem. Factorial isn't an overly difficult example, but in any case, so we've introduced this idea of a method, and we've introduced this idea of iterative solutions versus recursive solutions. Now, based on what we know so far, are there equivalents to methods in Game Salad? Behaviors. So again, what's a method? A reusable chunk of code. Every one of our behaviors is really, we don't know how many lines of code are behind the thing or how many different little, widgets it takes to build up that behavior, but changing an attribute, that's something we've done a lot. And we don't care how complex it might be behind the scenes. Whoever wrote Game Salad had to figure out what it meant to change an attribute and how you access those global attributes versus local attributes, all that stuff. We just know that when we call upon that behavior, an attribute gets changed. Same thing, display text. That's something we do a lot, right? We're going to see in here that you can write your own behaviors in Game Salad. You can create custom behaviors, so you can write your own methods. Okay?
So we have an answer for the question rule which you asked before.
Say this one more time.
This is the answer for the rule. The question we had last time with the rule. Whenever a value goes into a for loop, it doesn't change. When the loop is complete, it will remain the same till we go to the end. So that's why it doesn't affect from the value changes outside the loop, outside the rule.
Well, I guess this is one of those situations where I'm going to say yes and no. Yes, it's true what you're saying. It's unrelated to this. That has more to do with how the rule behavior works in Game Salad, in that it only fires. Oh, that's right. At the end of class, I asked the question, right? Okay. So what was my question? The question was why is it that the people from Game Salad chose to make a rule only fire, a rule associated with a attribute, only fire when that attribute changes? What's the rationale behind that?
So I think that it's a do or otherwise option in the rule as well. So we can compare it with the for loop in this, because when we enter a variable in rule, it works accordingly because the variable don't change. If there's some changes outside the rule, it doesn't change. It doesn't give you matter.
Right, but so if we have something like this. Let's just say my num equal 5. Just we're asking that question, and this guy is inside. Clearly, a rule is red in color, correct?
Sure.
Oh. Come to front. Aha! All right. So this is our rule, and this might be our question. And if that question is true, display text or something like that. We know that when we first start up Game Salad, we ask this question right off the bat, and we get an answer. Regardless of the answer to this, right? We know, we've seen several times, that question gets asked immediately one time. But we know that, for instance, in our ball launch game, that only after we hit the start button does something alter. Okay? Why is it that the makers of Game Salad decided not to even fire this rule a second time until the attribute that it's questioning changes? let's ask the alternate question. If it asks that question every single game cycle probably being 24 times a second or something, so related something to how many frames per second a human eye can see. Okay, so let's just say it's 24 times per second is what the game loop runs. Rather than ask, what would the downside be of asking this question 24 times every second?
Performance.
Yeah, performance hit, right? Now, if we only ask this question, if we only waste our time asking this question when that attribute has been altered, okay, we don't necessarily know if the value has changed. Somebody may have said change attribute from 5 to 5, okay? This guy would still fire. Why does that make sense? Well, we're only going to ask the question from a performance perspective if that attribute has changed. But that has its own ramifications. Somebody has to be paying attention to attributes and when they change. Specifically this attribute. Isn't that the same kind of performance hit? We can ask this question every single time, or we can have a dude over on the side that every single time through our game loop says, has this guy changed? Has this guy changed? Has this guy changed? Has this guy changed? What's the difference?
I think depending on the behavior that is in the rule, it could have really annoying. If it checked for that number every time, and the number had not changed, so if it was 5 every time, and it wasn't something small like display text, if it was destroy this item or do something like drastic, and it kept doing it over and over again, that would be a larger performance hit than just having it whenever it changes.
Okay, especially if there was an otherwise. It may also play into being difficult to write the logic that you want to be able to write. If you have an if, else, and otherwise. So if you're asking the question and when the question's false, that is, when the attribute has not changed, the question's false, and you're doing something every single time, even if it's just displaying the text again. Just to give you an idea of that, I'm going to come up here into our main method. And I'll just say something again that I think I've said before. All programs begin and end with main. Okay? Just something to store in your head somewhere. It'll become a more important factoid to remember throughout your computer science career, but it's worth restating now. I'm going to write a for loop for int I is equal to 0, I is less than a billion. Is that right? Is that 100 million? It's 100 million. Good enough. I think it's 100 million.
No, it's not.
10 million?
Yeah.
10 million. There. Now it's 100 million. Aha! And we're going to create a variable, int sum is equal to 0. And each time through here, we're going to say sum is equal to sum plus I. And at the very end, we'll display whatever sum is. So this loop's going to go through all the numbers between 0 and 100 million, add all those numbers up inside of a variable called sum. Actually, we'll get too big for the sum, but that's inconsequential here because sum's an integer, so it can only hold numbers up to 4 billion. Unimportant for what we're doing here, though. So we're going to do that, add all the numbers up between 0 and 100 million, and then in the end, print it out once. So we're going to run this program. How long did that take to run? Imperceptible amount of time, right? I'm going to move this line. I'm not even going to do the math. Instead, I'm just going to print out every number. So I took the complexity of adding out. I should gain performance there, right? How long is this going to take to run?
A while.
A lot longer, right? Very, very, very noticeably longer.
It's still got a ways to go.
Yeah. Much slower, correct? I/O, specifically, input-output, that's displaying stuff to the screen, reading stuff from the keyboard, whatever, is probably, pound for pound, the most inefficient thing a computer program could do. It seems so simple because so much of our computing experience involves displaying stuff to the screen, reading stuff in from the user, recording stuff from mouse clicks, that kind of stuff. It is horrifically expensive. Part of that is because our processor has to get interrupted every single time we need to get I/O. So for instance, as we're going through this 100 million times, every single cycle through our CPU, well, it's probably every several cycles, however many cycles it takes to increment the value by 1 and all that stuff. But very, very often, the CPU says, I need to pause for this program so he has time to display something to the screen. Once he's done displaying something to the screen, we come back to our program, add 1 to it, pause, display something to the screen. So our CPU is going through something called context switching. You learn about that in our operating systems course. What is the job of a CPU? The job of a CPU is to fake out the end user. We go back to single core CPUs. Now our CPUs have dual and quad cores in them, right? Now we even have dual quad cores and dual 6 cores and blah, blah, blah. But in a single core CPU, a CPU can literally only do one thing at a time, even though we think a lot's happening at once because it works a little bit over here, a little bit over here, a little bit over here, then goes back over here and does this. And it's all happening so quickly that the human eye, that we don't recognize that things aren't happening at the same time. Now we're experiencing it because a very expensive task at the CPU level is this idea of context switching, which means the CPU needs to put everything related to this program on hold. So it can pause, so it can go do its I/O, and it moves on to another program. Brings that back onto the CPU, puts everything back to where it was, and keeps going until it pauses to bring this guy back on. A lot of moving parts to accomplish something that does not seem very complex. And our program is still running. Make sense? So this is a very, very, very intensive program, even if in simplicity. Yeah, I mean, put your hand there. You can feel how hot my keyboard is.
Yeah.
That CPU is working from doing next to nothing here. Okay? So we'll go ahead and stop this program. All right. Always a bad sign when you have to hit stop to stop your program before your program completes. All right. So, given that, just kind of an interesting thing comes down again what he was mentioning about performance. We have no way of knowing how much complexity or whatever the programmer's thrown inside that rule. So we know that it might be almost a wash between checking the attribute over and over again in a way that the people who wrote GameSalad can control versus asking the question over and over again. What we can't control is what the programmer put in for their 20 behaviors they want to happen as a result of that that rule. Now the reality is what they did to check to see if an attribute has changed is probably relatively efficient compared to a rule. They've probably done something with like a mathematical switch or something like that where it's almost like a dam for water. And as soon as something changes, it opens up and lets things fall through rather than having to ask the question each time. So, but it's fair enough for us to assume they're equivalently complex, but at least we control everything on one side of the coin versus who knows what randomness on the other. Okay, so here are some examples of our factorial. Now, what we want to do, I'm going to go out to our scenes. I'm going to add another scene. We're going to call this scene factorial. So, screen 1 of our game, we do golf ball launching. Screen 2, it's factorial. As soon as our ball hits the ground, then we switch over and solve factorial. It's an instant classic on the App Store. Okay. So here's our factorial scene. We want to have a situation. Notice all our actors are still here because the idea is in most games, same actors exist between multiple levels. So, Mario's and all the levels. Not here. whole new actors. So we're going to call this guy answer. Okay, we'll throw him out on the screen. And we want to solve the factorial problem here. And we want answer to display the answer. Now we know we can build in a little interface for the user to put in, what I want to calculate the factorial of 4 or 5 or 6 or 7, whatever. So we know we can do that. So for right now, we're just going to make it a game level attribute. And we'll just make this guy an integer, and we'll call it factorial. And just for our example, we'll start off at 4. So our input is 4. Okay? And if we want to calculate a different factorial, we'll come in here and change it. So what we want to do is when we hit play, we want this guy to display the factorial of whatever this number is. How would we solve that problem? Using the game salad world. Well, I'm going to need to count from this number down to 1, or at least down to 2. It's going to involve our rules.
We're going to have a loop that subtracts 1 every time that is larger than 1. And then also applies it. I think we'll need another attribute besides just our factorial to get the answer.
Okay, so let's start off with what you said at the beginning. We need a loop. How do we simulate loops in Game Salad? Rules are asking questions. Timers, yep. So we'll go inside of our, answer actor here. And we're going to go ahead and put a timer. Now, what's different in Game Salad is Game Salad lives in an abstraction above the CPU. So with our CPU, like we just ran that Java program, that program is going to potentially run at different speeds on different computers. So this is a pretty fast computer here. So when it did all that math and just added all the numbers up between 0 and 100 million, and it seemed like it was almost instantaneous. If we take a much, much older computer, like let's say a computer from 6 or 7 years ago, it may have seemed like it took 2 seconds, something like that. Okay. Still fast comparatively, but a noticeable time difference. But in that case, we are at the mercy of the speed of our CPU, right? In this case, we've abstracted that. We don't directly benefit from our CPU being faster or slower with loops. Instead, we have to do something every so often, some number of seconds, right? We could do it in solid seconds, or we can do it in fractions of a second if we want. Well, how many seconds do we want this guy to take? Let's, for this example, we'll accept a little bit slower performance, and we'll say that this guy can happen every 1 second. Whatever he's going to do happens every 1 second. How many seconds is this guy going to fire for?
If it's every 1 second, it'd be
Okay. So it'd be 3 or 4 seconds, depending if you stop at the 2 or go all the way to 1, whatever. So are we going to fire for factorial number of seconds? Maybe factorial minus 1 number of seconds? So notice we have a little function thing here. Previously, we've always said, we've put numbers in here. So we're going to do something for so many seconds. How many seconds are games factorial number of seconds? 4, 3, 2, 1. Okay? So we're going to do something for that many seconds. Now, what are we going to do each time? Probably going to need to have a separate variable. If we look back at our code here, n came in as a parameter. So this is equivalent to our factorial attribute that we have in GameSalad. Yet we built up our answer somewhere else. Okay, we didn't change n. We used n as our base. So our timer is going to run for n seconds, like we have there. And then each time through, we're going to say our answer is equal to our answer times something. So what we're going to do is come back into GameSalad. We're going to add some attributes. I'm adding it to this actor because we can deal with them locally. The only one we need is our input from the global. So the attribute we're adding is going to be called answer. Okay, and we want answer to build up as we go through this loop. Correct? Okay. Now, what's going to happen to answer each time through this loop? Go back to our Java code here. Each time through the loop, answer became whatever answer currently is times some counter. I will be 4, then 3, then 2, then 1. So I is the current countdown from our timer. Does that make sense? How do we access that? Well, if we're matching this to the Java code, we currently have an n. We call that factorial, correct? We currently have an answer. We call that answer. What are we missing?
I.
We're missing I. What does I start off at?
Whatever. Factorial.
Same thing as factorial. So we're going to come in here. First, we're going to add an attribute to our answer actor. We'll just call this guy I. And we're not going to set it here. What we're going to do is we're going to change an attribute right off the bat. And again, this is an action, so it happens once and only once. What attribute are we going to change? We're going to change this guy's I attribute to be equal to our game's factorial attribute. Make sense? Okay. Then, what are we supposed to do inside here? Each time through, we're supposed to take answer, set it equal to whatever it currently is times the value of I. We'll change an attribute. What attribute? We're going to say our answer's answer attribute will be equal to whatever it currently is equal to times I. Okay? After we do that, then what are we going to do? Go back to our Java code. I needs to become 1 smaller than it used to be. So we'll change another attribute. Change I to be whatever I currently is, minus 1. Make sense? And then each time through, well, as a persistent behavior, we're going to display answer. Oh,
Just select the scene on the bottom.
I think I can, as long as I start it at the scene level. Let me save this real quick. It's acting a little funny. Okay, so it's currently set to 0. Well, what was my factorial? The game level, my factorial was 4, right? So what should it say? It should say 24 if it's done this correctly. All right. Well, let's go back into our actor. Answer. Our timer says do something for this many seconds. What happens if I click run to completion? It's not going to make a difference, but let me... All right. So this goes back to the same issue we're having with when rules fire and when timers fire. All of our logic is doing the correct thing right now, isn't it? Everything in here says do what our Java code said to do. But we need to work around this idea of attributes changing to fire things. Make sense? All right, so the same thing we've been talking about with rules. About knowing when an attribute changes. So, for Friday, use GameSalad to solve the factorial problem. All right? Include a screenshot of your behaviors in here, as well as a screenshot of your finished thing showing 24 or whatever the output is for whatever factorial you chose. That way you can't just throw a box in there that says
24.
24. That's what it is. This guy displays text 24. All right, I'll put that up on Angel now, and I'll see everybody on Friday.